All right, we're going to do 2.3 now, the precise definition of a limit. What we need here is basically a more precise definition. Remember in the last section we did an informal definition, and now we're going to do something a little more precise. And this is actually pretty useful in the sciences, the techniques we're about to learn here. So especially if you're in the science area, you're really going to want to pay attention to this. So we need a more precise definition in order to prove limit properties. Plus, like I said, it's also going to be pretty useful. Here's the idea. To prove that the limit of f of x as x goes to c or approaches c equals L, you need to show that you can get f of x as close as you want to L by making x close enough to c. All right, so we're basically showing that if x goes to c, then we're also going to end up getting f of x going to L as long as we get close enough. So consider the function y equals 2x minus 1 near x equals 4. Intuitively know that the limit of 2x minus 1 as x goes to 4 is just 7, because that's just 2, because there's no hole or anything there, nothing getting messed up, so it's just 2 times 4 minus 1, which is 7. You're just plugging that 4 in. However, how close do you have to get how close does x have to be to 4 so that y differs from 7 by less than 2 units? And so if we look at that, we've got this right here. And you can see that here in the blue line, right, this blue line right here, drawn on top of, that blue line is our function. And basically what we're saying is that we are going to be within 2 of 7. So we have to be within 2 of 7. So that's as low as 5 and as high as 9. That's like our tolerance. We have to be within that range of values. And if we do that, we can come across and see that to get a 5, we're going to have a corresponding 3 for that. And to get a 9, we're going to have a corresponding 5 for that. And so in this case, anything in between 3 and 5 that we plug in for x is going to give us an output value between 5 and 9, which would be what we wanted. So that's looking at it graphically. But what if we look at it, algebraically, mathematically? So let's take a look at this. What we want is we want f of x, our function, minus 7. That's the value we're plugging in right here, all right? We want that to be less than 2. So in other words, we're going to go to this value right here, this f of x value. We're going to subtract 7 and put it down to here, and then we want to be within 2. So we want the absolute value. So we're going to be between 2 and negative 2, but we're taking the absolute value. So if we end up with like negative 2 or negative 1.5, it'll be positive 1.5. So we're trying to then say we want to get within this range if we subtract 7 off. So we're going up here, finding f of x, dropping down to 0, and then we want to be within 2. All right? And so our function is 2x minus 1. So this is 2x minus 1 minus 7 has to be less than 2. And so this is 2x minus 8, absolute value, has to be less than 2. What this means is that 2x minus 8 has to be less than 2 or greater than negative 2. Because if we get like a negative 2, we take the absolute value, we're up to the 2, we're okay. Or negative 1.5 becomes 1.5, and we're good. So this is where we have to be. So now we're going to go through and we're going to add 8 to everything. Plus 8, plus 8, plus 8. And this gives us 2x has to be less than 10, has to be greater than 6. And then we can divide everything by 2, divide by 2, divide by 2. And what we get is that x has to be between 5 and 3, or 3 and 5, which is what we see right here graphically having done it, okay? And so that works right there. As long as we give a value between 3 and 5, when we plug it in, we will end up getting a value of an output between 5 and 9. And if you want to test that, you could try 4 if you wanted. So you could do 2 times 4, just plugging it into the function, right? That was our function, is 2x minus 1. And you could do 2 times 4 is 8, minus 1 is 7. And that puts us right there. We could also do something like, say, 2 times 3.5 minus 1. What's that going to equal? 2 times 3.5 is 7. 7 minus 1 is 6. 6 is right here, and that's within our range of 5 to 9. Okay, so values inside that range will keep us inside that range. So a little more generally, think of this process as a game if you want, and you're wanting to prove that the limit of f of x as x go to c equals L. So essentially what's going to happen is, you tell me I want to stay within a certain, what we're going to call epsilon. That's the Greek letter epsilon. I forgot the S. Epsilon units of L. So we want to stay within that amount. That would be up here on the vertical axis. That would be the epsilon. Okay, and so like this is epsilon, or this is epsilon. We want to stay within epsilon of L, and then I'm going to then tell you, you must stay within delta. That's another Greek letter, lowercase delta, units of c. And this is the delta down here. The delta, one way or the other. Actually, this is delta and this is delta, not the whole thing. Okay? So that's essentially what's going to happen, and that's what we're going to try and figure out how to do. So let's define this. So definition, let f of x be defined on an open interval about c, except possibly at c itself. Because remember, we're taking the limit as it goes to c, not right at c, so we don't actually have to have it defined there. We say that the limit of f of x as x approaches c is the number L, and we write it just like we've been doing. Limit of f of x as x approaches c equals L. If for every number epsilon greater than 0, there exists a corresponding number delta greater than 0, such that for all x, absolute value of x minus c is going to be less than delta. So we're going to be within that delta range, right? We're going to be somewhere in here. And then what that's going to do is then be true if that's true, then it's going to give us an f of x minus L, right? Absolute, that's within epsilon of whatever L is. So if we're in this range, we'll end up in this range, is what's that saying, where this is the blue, right? That's the red. So if we can do what's in the red, we'll end up staying within the blue. But the way this is going to be done is you will be given an epsilon. You're going to end up computing L, because that will be our limit. So you'll find the limit, and then you'll compute it, and then we're ultimately going to find this delta that we'll have to have in order to keep us within that certain amount of our L function, of our L value. All right, so how do we find this algebraically? First thing we need to do, this is all written on the previous page, so let's just start with step 1. You're going to solve the inequality f of x minus L is less than epsilon to find the open interval AB that containing x naught on which the inequality holds, okay? Then what we're going to do is find a value delta greater than 0 that places the open interval x naught minus delta and x naught plus delta centered at x naught inside the interval. All right, the inequality f of x minus L, the absolute value of that, is less than epsilon, will hold for all x not equal to x naught in this delta interval. Okay, so let's try this. Just let's start off a little slow here. So sketch the interval AB on the x-axis with the point C inside it. Then find the value delta greater than 0 such that for all x, the x minus c absolute value will be greater than 0 and less than delta, and a will be less than x, which will be less than b. So let's take a look at this. So let's draw our number line, okay? And what we're going to have here, a is supposed to be 1. So 1, 2, 3, 4, 5, 6, 7, just like that. And 7 is what b is. So this is a, this is b, and then they're telling us that c is at 5 right there. Oop, no, that's not 5. That's 4. C is at 5, right? So 5, and this is 7, and this is 1, right? Maybe I'll know the whole thing's there. That's where I got those values right there. They're given. And so we want 5 minus delta and 5 plus delta to be in 1, 7. All right, that's A, B, right? We want to be within that 1, 7 range. So what value of delta, what delta would do that? So what delta would do that? Well, if you look, if we look at 5 and 1, we can see that we can go all the way to the left 4 units, right? 1, 2, 3, 4, and we're still within A. But if we go to the right 4 units, 1, 2, 3, 4, we're outside of B. All right? So you have to think not just about how far you can get to stay within one of them, but what's the furthest you can go in either direction without going outside it. And so if we look at that, we can go 1, 2 towards B, and that keeps us within B, and we can go 1, 2 towards A, and we're still within that range. So the maximum amount that we can move away from 5 is going to be 2. So that answer is going to be 2. And the way we can think about this is we can basically say that delta is the minimum value of A minus C or B minus C. Okay? Whichever one that we can start at C, right? Which I realized just now that I wrote a 5 there. Or no, maybe that was supposed to be a B. I don't know. That's supposed to be not a C. That's not a B. That's a C. There we go. So what we're going to basically do here is say, all right, whichever one is closest to C, however far away it is, that's the one, that's the distance we can do, and that's the maximum we can go and stay within the interval. Okay? And so we'll have minimum of A minus C, so absolute value of 1 minus 5, and the absolute value of B minus C, which is 7 minus 5. And so now we've got the minimum of 1 minus 5 is negative 4, absolute value is 4. 7 minus 5 is 2, absolute value is still just 2. And so we have to take the minimum of 4 and 2, and that's 2. So that's doing it there algebraically, or at least just by finding differences rather than just looking at the number line. It's whichever one keeps us, or whichever one is closest to our C value, that's however far away it is, that's the furthest we can move. All right, so let's try one of these. Here, we're given that the limit, all right, as x goes to 5 of the square root of x minus 1 equals 2. Find a delta that works for epsilon equals 1. So here's what we're given. All right, let's label these things. First off, here's epsilon. That's given. All right, this is L. This is our limit. That's why we're using L to define it. That's our limit. We have to be within that. We have to go towards that point. That's this 2 right here. Maybe I'll highlight here. This 2, that's that 2 right there. Our epsilon, right? Our epsilon equals 1. That's this distance here. That's epsilon, or this distance here. Okay, that's where we're wanting to stay within. And then C is that value right there. That's C. Okay? That's C. So let's, because that's the value that x is going towards, so I should highlight that too. Here's C. There we go. And what we want to find is this delta here, that way or that way. That's our delta. All right? That's what we're trying to find. What is that delta? Okay? So let's start with this. So let's first start step 1. Let's solve f of x minus L is less than epsilon. All right? And so we do this. Well, our function is square root of x minus 1 minus L, which we found up here was 2. And epsilon, which was given, is just 1. And now we can go through, get rid of that absolute value. Square root of x minus 1 minus 2 is less than 1, but greater than negative 1. So then we're going to add 2 everywhere. So this becomes a 3, and this becomes a 1. And then we can square everything. That becomes a 1. This is x minus 1. This is 9. This is 9. And then we can add 1 to everything. So x becomes 10 and 2. So there's where we have to stay. We have to stay between 2 and 10. And now we have to figure out how far away can we get from that. And note that this is A, this is B, and remember, C was up here. So we check and see. Delta is our minimum of C minus A or C minus B. It doesn't matter if I do C minus B or B minus C because we're taking the absolute value. It's just the difference between the two. So this will be the minimum of C minus A is going to be 5 minus 2, and this one's going to be 5 minus 10. And then it's going to be the minimum of the absolute value. 5 minus 2 is 3. Absolute value is 3. And then 5 minus 10 is 5. So it's between the minimum of 3 and 5, which is just 3. Okay? And so that's what our delta is going to equal. It has to be 3. And you could do the same thing looking back here. We know that we're at 2. We're over here at 10. And this is at, C is at 5. Right? And so if we look on a number line, it's like 2, 3, 4, 5, 6, 7, 8, 9, 10. We see here that we're 1, 2, 3, 4, 5 away from 10. That's that 5 we got there. And we're 1, 2, 3 away from 2. That's that 3 right there. So this was 3, right? And this was 5, starting from there. And we took the minimum of those two. Okay, and that's what this little algebra there on the right does for us, is we don't have to draw that number line out. All right, let's take a look at this one. So given f of x equals 3 minus 2x, c equals 3, and epsilon equals 0.02. All right, so now the training wheels are starting to come off. We're not being given the limit. We're going to have to find the limit. So let's start with that in part A. Part A, we're going to find the limit, and we need it to go to c. So it's going to c. This is c. Okay, so let's find that limit. So we want the limit as x goes to 3 of 3 minus 2x. Okay, we want that limit. Here, we can just go ahead and plug this in. This is going to be we can plug this in because we have nothing crazy going on. This is going to be 3 minus 2 times 3, which is going to be 3 minus 6, which is just negative 3. And that's going to be our L value. So there's L. We found it right there. In part B, it asks, find a number delta such that for all x, x minus c is between 0 and delta, which implies that f of x, the absolute value of f of x minus L, is less than epsilon. So let's go ahead now. Now we have L, we have c, we have epsilon. So now it's back to being like the problem just before this one, after we first found just the only difference here in this one is we had to find the limit ourselves instead of it being given. F of x minus L has to be less than epsilon, okay? And so remember, that's us saying, hey, we have some function, here's L, and we can go down an epsilon amount, so this is L minus epsilon, and we can go up to L, oops, that wasn't a good L, L plus epsilon, okay? So we have to stay somewhere in there. We're going to come across here. We're going to look at our function. And we're going to see what values show up here for x. And this is going to be, basically that's going to be c. And this will be like plus, whatever delta is going to keep us within that range. It doesn't have to be symmetric. It might be one side on delta is further away than another, and we're going to end up staying within it. All right, so let's plug this in. So this is 3 minus 2x right there, minus negative 3 for L, less than epsilon. And we can go ahead and get rid of that absolute value and do this. So this becomes a plus a 3. So this is going to be 6 minus 2x. Has to be less than epsilon and has to be, not epsilon. I forgot to write in what epsilon actually is there. Epsilon was this 0.02, 0.02, 0.02, and negative 0.02, just like that, to get rid of our absolute value. Now what we can do is subtract 6 from both sides. So this will be negative 6.02, negative 2x less than, and subtracting 6 is going to be, what, negative 5.98. Then what I'm going to do is divide everything by negative 2. All right, and when I divide by negative 2, this becomes 3.01. This becomes just x, and this becomes 2.99. And remember, we divided by a negative, so we have to reverse our absolute value sign. So dividing or multiplying by negative, you flip, not your absolute value, you flip your greater than or less than signs. And so now we've got that this is A, this is B, and remember C was given right up here, there's C. And so we need to check for delta. Delta is going to equal the minimum. The minimum, basically, the minimum of whichever is closer, whichever between A and B is closer to being C, and how far apart they are. So here in this case, we'll have absolute value 3.01 minus 3, or absolute value 2.99 minus 3. Okay, just the difference between them. And again, it doesn't matter if I do 3.01 minus 3 or 3 minus 3.01. As soon as I take the absolute value, they're going to be the same. So this will be the minimum of, and this is going to be 0.01, and this one's also going to be 0.01 once you take the absolute value. Okay, and so the minimum of 0.01 and 0.01 is just 0.01. And there you go. There's our delta value. Okay? So after this, we've got some that I'm going to leave for you to try. If you go back and check the notes, I'll have these worked out for you. But try taking a look at some of these. And here, take a look through these things. Here you go. Try these ones and see how you do. And then this last one, I think I'm going to make a separate video just specifically doing just this problem. So be sure to take a look for that one as well. All right, that's all.